Okay. Anyway, well, there we go. Okay, so now we're starting this chapter, the next chapter that is. This here will be on more probability. And we're also going to learn different methods for counting. Okay. I mean, for instance, if you look at the events that we saw so far, wait, am I recording? Oh, what the? Stop sharing? Okay. If you look at the events that we saw so far, okay, we were looking at the probability of a certain event happening, right? That's what we were looking at. The probability that this event happens, the probability that another event happens. Here we're going to kick it up a notch and we're going to consider now the probability of two events happening, the probability that this event happens or that event happens. For instance, we'll see this. If you're rolling a die, a standard six-sided die twice, what's the probability that the first roll you roll a 6 and on the second roll you roll a 6? We're going to see how to calculate things like that. It's fun. At least I think so. We're also going to see what it means. I mean, related to that is the idea that two events are independent or mutually exclusive. You'll see what I mean by that. I mean, essentially with mutually exclusive, if I remember correctly, it basically means they can't happen at the same time. But because we're kicking it up a notch, we can't really just list the sample space, though, in order to determine how many outcomes there are. I mean, before we can do that, like for instance, if we were tossing a fair-sided coin or rolling a standard six-sided die, you could list all the outcomes of an event and the sample space. However, realistically, with most experiments people do, you really can't list all the outcomes. But then how can you determine how many there are? Well, that's where we have counting methods coming in. Or if you did try to list them, you can use tables and tree diagrams to help organize them. So if you did try to list them, people would use tables and tree diagrams. But if you're not able to list them, but you want to know how many there are, that's where we have these counting methods. And they do come in handy. So I said before, I think I misspoke. You could try listing all the outcomes of a sample space. It might get tricky to do. That's why people have tables and tree diagrams to help list them more effectively. But generally, you're not going to be able to list them. There's just going to be too many. You could have hundreds or even thousands of possible outcomes. Well, I don't want to list 1,000 things. I mean, you could theoretically do that, maybe using a table or a tree diagram. But if you're like me and you don't want to list them all, you're going to use special counting techniques. Okay? And that's where these permutations and combinations come into play. All right. Anyway, first we're going to look at what it means for two events to be independent. And this is the definition. Basically, they're independent, two events A and B, if the probability of event B occurring is the same whether or not event A occurs. In other words, two events are independent if whether or not one event occurs does not affect the probability of the other one. You know, independent, their probabilities don't depend on each other, if that makes sense. Okay. All right. So for instance, we've considered before tossing a fair coin and rolling a six-sided die, right? You know, we have done that before. So let's suppose A is so let's consider the experiment where we're going to flip a two-sided coin, okay? Then after that, we're going to roll a standard six-sided die. Now, let's let A be the event. The coin lands heads up. And we're going to let B be the event that we roll a six on the six-sided die. Well, how can we find the probability of those? Well, let's list the sample space. Here it's actually not too bad. So yes, I know I just said you really don't want to list the sample space. Well, for this experiment, it's not terrible. You can see there's only 12 outcomes. You know, from the coin, you're going to get heads or tails. From the die, you can get and you can get 1, 2, 3, 4, 5, or 6. So you could list all the outcomes. Not terrible. Basically, what I'm going to do here is determine if A and B are independent. Okay. So B is the event that we roll a 6, right? That we get a 6 on a standard 6-sided die. Okay, well, when does that happen? Well, here it happens. We get a 6, right? When I'm trying to circle. Ooh, that's nice. It also happens here, as you can see. So these are the two outcomes where we roll a 6. Well, there's 12 outcomes altogether. 2 of them correspond to event B. You know, B is the event that we get a 6. That's what it says here, right? B is the event that we roll a 6. So because of that, the probability of B would be 2 out of 12. Which, remember, is the same as 1 over 6. I mean, this might be a little, it might be a little strange that I'm reducing it, because if I remember correctly, I said last time, people generally don't reduce fractions when working with probability. But for now, let's just do that. I mean, it's not wrong to reduce it. It's just that people generally don't do it. Okay. So this was B. What if event A did occur? Remember, A is the event that the coin lands heads up. Right? Remember, we're flipping the coin first, then we're rolling the die. Well, what if the coin landed heads up? Well, then we're only focusing on these outcomes here, right? Because we got heads up, as you can see. Okay, well, now what's the probability then we get a 6? Well, here there's only one outcome out of 6, so the probability of B now would be 1 over 6. So again, this is assuming event A occurs, okay? Well, one second. This is assuming event A does occur, okay? So we know the coin lands heads up. So let's say we know that. So we know that the only possible outcomes then are these. Okay, well, in that case, what's the probability that we get a 6? Well, this is the only one that has a 6 in it. So we would get 1 out of 6. Does someone have a question?
Yes. What determined that we were gonna throw the coin 6 times? Was that like?
No, we're rolling the die 6 times. We're rolling the die once, and we're tossing the coin once. These are all the possible outcomes here.
Mm-hmm.
Okay, so like let's say we're just considering this. Well, we want to know what's the probability that we get a 6 on the die. Here we're saying, okay, so let's say we know that the coin landed heads up. So these are the only possible outcomes. How likely is it we're going to get a 6 on the die now? Well, this is the only one that has a 6. So we get 1 out of 6.
Mm. Okay.
It's almost like here we don't know. It's almost like here, well, we don't know if we get heads or tails on the coin. Well, let's play it safe and list every possible outcome, right?
Mm-hmm.
And that's what we do. That's what we're doing here. Well, how likely is it that we're going to get a 6 on the die? Well, the only way that could happen is if this occurs, right? You get heads on the coin and we roll a 6. Or we can get tails and the 6 on the die. Well, that's 2 out of 12 outcomes. So that's the probability of B.
Okay. Thank you.
Yep, you're welcome. I hope you understand it. You may have to think about it a bit. Not trying to dismiss you. I mean, I know this is not easy. I know this is not easy stuff.
No, I know. I guess
Okay.
it takes some examples.
It will. That can happen. Okay. So we're solving it this way. Okay. But let's say we know that, well, so let's say A did not occur though. We're trying to show again that A and B are independent. What if we said, well, A did not occur? We were wrong. The coin landed tails up. Then what? Well, then we knew our sample space had to be this. So maybe this will help. We're basically trying to see if the events A and B are independent. We found event B. We got its probability. Okay? But we have to see, will this probability depend on whether A or B, whether event A occurred or not? Well, if event A did occur, the coin landed heads up, well, then these can only be our possible outcomes. Because these have a tails in it, but the coin we knew landed heads up, so we can disregard these. And from here, we get 1 out of 6, because that's the only outcome here where we roll a 6. But let's say we were wrong. Let's suppose A did not occur. The coin didn't land heads up. Let's say it landed tails up instead. In that case, these are our possible outcomes, right? The coin landed tails up. So these are the only outcomes we would care about then. Well, now how likely is it we can roll a 6? There's only one event here. This one that has a 6 in it. So in this case, the probability would be of B would be 1 over 6. But notice that the probability of B did not depend on whether event A occurred or not. Okay? It did not depend. No matter whether A occurred or not, we got the same probability. This shows events A and B are independent. That's really what I'm trying to show here. I mean, I understand it's a little bit confusing. It's really not the most efficient way to show A and B are independent, but we will learn later on how to actually show a more efficient way, that is, to show events A and B are independent. I mean, here I'm just showing you the way from scratch, so to say. I know this is not efficient, but I really hope everyone gets some kind of idea about this. Again, I know this isn't easy. I'm not trying to dismiss anyone. I understand this is not easy stuff.